Hello. In the last lecture, we have learned about the classification of isometries of hyperbolic plane. So in this lecture, we'll learn about the discrete subgroups of isometries of hyperbolic plane. So these discrete subgroups of isometries of hyperbolic plane are called Fouchian groups. Okay, so let me begin. Okay, so I'll be defining this Fouchian group in a short while. So before that, so let us see what you mean by a discrete subset of a topological space. So let us begin with a topological space. So let X be a topological space and A be a subset of this X. So the subspace, so when I say A is a subspace of X, it means that the topology on A, it is a subspace topology induced from X. The subspace A is said to be a discrete subspace of X if, so if the following holds, if for, so any sequence xn in X such that xn converges to a point of A, so then, so this xn, it is a eventually constant sequence. So then, so there exists a natural number n, 0, such that, so this xn, so this will be equal to your A for all n greater than equals to n0. So this means that, so this definition of discrete subspace, it means that, so A does not have any limit points in X. Yeah. So A does not have any limit points in X means that, so if I take any sequence in X which converges to a point of A, so then that sequence will be an eventually constant sequence. So that is the meaning of it does not have any limit points in X. Okay. So now let us move to the Fouchian group part. So we have this group SL2R. So what is this group? It is the set of all 2 by 2 real matrices such that the determinant of this matrices are 1. So you can take this matrix. So this you can think in terms of this uh, this this point. So this matrix A, B, C, D, you can take it as a point in R4. So R4 has this usual topology. And so this SL2R, it is naturally it is a subspace of this R4 with the help of this map. So therefore, so this SL2R has subspace topology induced from R4. Okay. So therefore, on this group SL2R, we have a topology coming from R4. And what is my PSL2R? So we'll be interested in this group. So this is this quotient group SL2R mod plus minus identity matrix. So we have a natural map from this SL2R to your PSL2R. So this Q, it is a quotient map. So now what is the topology on PSL2R? So the topology on PSL2R is the quotient topology. Yeah, so PSL2R, it is a quotient space. So if you put the quotient topology on this PSL2R, so this map Q, it becomes a continuous map. Okay, so we have put a topology on this PSL2R, and but in particular it is a quotient topology. And also we know that this PSL2R, it is a index to subgroup of isometry of this upper half plane. Yeah, so we'll be working with the upper half plane model. So disk model is isometric to this upper half plane. So PSU, so if you take the isometric group of this disk model into disk model, so we'll get PSU 1, 1. Okay. So now let us define what you mean by Fuchsian group. So a subgroup gamma of this PSL2R, or you can put PSU 1, 1 here, is said to be a Fuchsian group if gamma is a discrete subspace of this PSL2R. Yeah. So this is the definition. So if I take any discrete subgroup of PSL2R or PSU 1, 1, so that group will be called to be Fuchsian group. Okay. So now we have this observation. This is very simple observation. So gamma, let us take it to be a subgroup of PSL2R. So gamma is discrete. So if and only if so Tn belongs to gamma, and suppose Tn converges to identity element. So this is pointwise convergence. So this will imply that so this Tn is equal to identity for all large n. Yeah, so this is very straightforward. So if you assume gamma to be discrete, and suppose Tn converges to identity, so identity it belongs to your gamma. So gamma, it does not have any limit points. So the sequence Tn has to be an eventually constant sequence. And for the converse part, uh, suppose you take some, so you want to prove that gamma is discrete. So suppose you take Tn converges to T, where T belongs to your gamma. So then Tn inverse, so if I take Tn converges to your T, where this T, it belongs to your gamma. So then, so T inverse Tn, it converges to identity. So T inverse Tn, it makes sense because gamma, it is a, or PSL2R, it is a group. So T inverse Tn, it makes sense. And by the assumption, so this sequence, it converges to your identity. So by the assumption inverse Tn is equal to identity implies T inverse Tn is equal to identity for all large n. So that will imply that this Tn equals to T for all large n. So that is the proof. Okay. And now let us move to the next thing. So now we have this following important lemma. So our next target is to prove that. So if I take any Fuchsian group, so this Fuchsian group, it will act on this upper half plane or your unit disk. So any orbit, so that will be a discrete set in the upper half plane or unit disk. So we want to characterize any discrete subgroup by the discrete subset of this upper half plane. Okay, so this lemma will be useful for that. So let us take Z naught belongs to your upper half plane and K be a compact subset of this upper half plane. So then, so this set E consisting of all those elements of PSL to R such that T of Z naught belongs to your K. So this is a compact set. So this is a compact set in your PSL to R. So what is the proof of this? So we'll be proving the following thing. So you take the set E1 to be T belongs to your SL to R such that T of Z naught belongs to your K. So we'll prove that E1 is compact. So once we prove that E1 is compact, and so we have a quotient map from this SL to R to your PSL to R, and Q is a continuous map. And Q of this U1 is equal to your E. So if you can prove that E1 is compact, so E1 compact will imply that U is also compact. So the claim is E1 is compact. Okay. So in order to prove that E1 is compact, so E1 you can think it is an element of R4. So we'll prove E1 is closed and bounded. So E1 it is a subset of R4. So any closed and bounded subset of R4 or Rn is compact. So if we can show that the E1 is closed and bounded, then we are done. So first job is to show that E1 is closed. So let us take a sequence. So let Tn belongs to your E1 such that Tn converges to T pointwise. So let T and Z So this is equal to your ANZ plus BN by CNZ plus DN. And we know that, so because Tn belongs to E1 it is a subset of this SL to R. So AN DN minus BN CN. So this will be equal to your 1. So Tn belongs to your E1. So it also says that Tn Z0, it belongs to your compact set K. So Tn of Z0, it converges to your Tz0. As K is compact, so this will, so K compact means K is also a closed subset of this upper half plane. So K is closed in upper half plane. So therefore, so T of Z0, it belongs to your K. So that will imply that, so T, it belongs to your E1. So that is the definition of my E1. So T is an element of SL2R. Tz0 belongs to K. So that is that collection. So therefore, this T, it will belong to E1. So this proves that E1 is closed. So next job is to show that, so claim is E1 is bounded. So let us take some element Tz equals to Az plus B by Cz plus D. It belongs to your E1. And we know that Tz, it belongs to your compact set K. So this will imply that because K is, again, it is a closed and bounded set. In particular, it is a bounded set. So this will imply that there exists a number, positive number M1, such that mod of Tz0 is less than M1. So that is mod of Az0 plus B by Cz0 plus D, it is less than M1. So let us write it to be equation 1. And so now also note the following. So suppose I take this map A to this R greater than equals to 0. So what is this map? You take any W belongs to K and take the map to be, define the map to be W goes to mod of imaginary part of this W. So as K is, so this map is continuous. So this is a continuous map. So K is compact in upper half plane. So let me draw this picture. So this is a compact set. So this K, it lies in this upper half plane. So K does not intersect this real axis. So because K is compact, so we'll get some number M2 such that the distance of K to this real line, it is greater than this M2. So yeah, so what we have, so this mod of, So there exists m2 greater than 0 such that this mod of imaginary part of w is greater than m2 for all w belongs to your k. Also note that so this k, it is a subset of this upper half plane. So always this imaginary part of this w is greater than 0. So instead of taking the mod, I can remove the mod from here. So what we have? So imaginary part of w is greater than m2 for all w belongs to your k. So yeah. So now we know that t z naught, it belongs to your k. So therefore, and which is nothing but equal to your a z naught plus b by c z naught plus d. So therefore, imaginary part of a z naught plus b by c z naught plus d. So this is greater than m2. So now we can work on this thing. So imaginary part of this a z naught plus b by c z naught plus d is equal to the imaginary part of z naught divided by mod of c z naught plus d whole square. So therefore, what we have, so mod of c z naught plus d whole square. So this is less than, uh, so less than imaginary part of z naught by m2. So I can remove the square from here. So I'll have a root here. So therefore, from 1, and let us call it to be 2. So 1 is this thing. So from 1 and 2 was what we have. So mod of is it not plus b is less than m1 times root over imaginary part of z naught divided by this m2. So yeah, let's call it to be equation 3. So from this 2 and 3, so I have taken this t to be an arbitrary point of, so t to be an arbitrary point of this E1. So A, B, C, D, so these are varying. So from 2 and 3, so what we have, so A, B, C, D, so we have A, B, C, D are bounded. So I have taken T to be an arbitrary Mobius transformation from E1. Tz equals to Az plus B by Cz plus D, where this A, B, C, D are bounded. So therefore, so this implies that E1 is also bounded. So therefore, what we have proved that this E1 is closed and bounded, and E is Q of E1. Q is the quotient map, which is continuous. So E1 is compact, so that will imply that this E is compact. So in the next lecture, so we'll learn about properly discontinuous action, and also prove the fact that so a Fauchian group, if I take a Fauchian group, so this is equivalent to saying is that so any orbit is finite in the upper half plane.